Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, ISC. Today's talk is by Dr. Vinod Prabhakaran, and he will be speaking on consensus capacity of noisy broadcast channels. Professor Vinod Prabhakaran is an associate professor at the School of Technology and Computer Science, Tata Institute of Fundamental Research, Mumbai. His research interests are in information theory, cryptography, and communications. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Prabhakaran directly or type them in the chat box and we'll moderate it with him. Over to you, Professor.
Thank you. Thank you, and thank you to Parimal and the other organizers for the invitation. This is joint work with Neha Sagwan, who's a graduate student at TIFR, and Varun Narayanan, who was a graduate student here, who is now a postdoc at Technion. And thanks to Neha for help with some of these slides. Okay, so let me start. Hold on a second. All right, there we go. Yeah, quick outline. So I'll briefly give an informal introduction to the problem, some motivation, and we'll formally set it up and present some results. We'll define what we mean by consensus capacity, and we'll present a feasibility result and illustrate some of the key ideas using the example of the Erasure channel. And then we look at the more full-fledged results and conclude. By the way, please, and as was mentioned, please stop me. I have a certain set of slides. I don't need to go through all of them. Please stop me in the middle and ask questions. And thanks everybody for turning up for this remote talk. Okay, so there are a few keywords on the title. So let me explain what we mean by all this. We are at the EC department, so let me start with communication. So this is an information theorist abstraction for point to multi-point communication channel. So there is a transmitter which can select one out of a set of possible symbols to send to the channel. And the receivers will receive random variables which are jointly distributed according to some joint distribution, which is no. We'll assume it is no. So this shows two receivers in the picture. That's what I'll do throughout the talk. But it turns out the results here generalize to more than two receivers also. And in case there are any computer scientists in the audience, I should mention that this is a noisy, I should point out that this is a noisy broadcast channel. So the whole point of the talk will be to realize noiseless broadcast from a noisy broadcast channel, as shown in the figure. Okay, so let's look at a communication problem. This is what's called a common message communication problem. Here, the sender has a certain message to send to both the receivers. The sender can make multiple uses of the channel. Here, denote that by N here. We'll drop this superscript later. So the sender transmits a code word corresponding to the message, which is an N-length vector. And the receivers from the received random vectors try to infer what message was sent. So this is a well-known problem, well understood. And the problem that we're going to look at today can be thought of as a variation on this. So here, our sender may not necessarily always send a code word. It might send any vector, any possible input vector into the channel. And we would still like both the receivers to agree on their decoder outputs. That is, they should have consensus. This is what we mean by consensus. And of course, when the transmitter, the sender, sticks to the protocol and sends a code word, a valid code word, we would like the receivers to agree on the message corresponding to. Now, this notion of consensus is motivated by a problem in distributed computing called the Byzantine generals problem. So the story for this problem is something like this. We have a set of generals. There is a commander who wants to send a message to her lieutenants on the battlefield. So the message might be attack or retreat. And there's a gang of malicious lieutenants who will try to disrupt us. So we want to make sure that all the honest lieutenants still get the message that the honest commander is trying to send. Now, the commander herself could be part of this malicious gang. In this case, we would like to make sure that all the honest lieutenants still agree on the same message. So they are attack together or retreat together. And the goal in this case of this malicious gang will be to somehow split bunch of honest lieutenants attack, a bunch of honest lieutenants retreat, and then get into trouble. So this is an old problem, and there's a lot of applications. So by the way, the way you would sort of achieve this, you imagine that there's some kind of underlying network over which these nodes, these generals can talk to each other. So this has a lot of applications in distributed computing, fault-tolerant distributed storage, certification authorities. Also, if you can realize something like this, it's a very useful primitive in secure multi-party computation and cryptography. Also, there's a lot of interest these days from blockchains. So, as you can imagine, it's an old problem with a lot of applications. There are a lot of variations which have been studied in the literature. I've tried to list some of them, some of the variations. So one thing could be, what sort of security do we want to? Can we make computational assumptions that the adversary is computationally limited, or do we want unconditional security? Do all the nodes share a clock? They act synchronously? Can they communicate synchronously or not? Can they randomize? We have a deterministic protocol. What is the nature of the adversary? Does the adversary go and corrupt all the generals once up front, or does it do adaptively as the protocol progresses? What can the adversary see? Can it even see communication between two honest lieutenants, for example? What's the nature of failure? So this is, as I said, this comes from distributed computing. So various failure modes could be just a server crashing, or some messages getting lost, or it could be something more malicious, like the story we've been telling, Byzantine. And even other considerations which I haven't put on the slide, like nodes may join or leave during the execution of the protocol, all kinds of considerations. And in terms of performance, we might be interested in what level of security can we provide? What is the number of, or fraction of parties who may be corrupt and still our protocol would work? What are the number of rounds the protocol needs? How much communication does it need to do? How much computation does it need? All kinds of considerations. So the first paper looked at a certain variation where private channels exist between every pair and want unconditional information theoretic security. They are synchronized, they have a common clock. Protocol they considered was deterministic, and the agents are Byzantine. So under these assumptions, the result, very interesting result, was that you need a strict 2/3 majority. That is strictly more than 2/3 honest majority in order to accomplish Byzantine consensus. So in particular, if you just have 3 agents, like in our picture, an honest commander, a commander and 2 lieutenants, they're all Byzantine users, then it is simply impossible, right? Even one of them being corrupt will prevent us from achieving Byzantine consensus. You don't have strict 2/3 majority. And so one way to get around this impossibility result is to assume, is to give up on information theoretic security. as to assume computational limitations on that. What we are doing, we can think of as getting around this impossibility result by making use of a stochastic resource, a broadcast channel in particular. So we're trying to see, can we still get Byzantine consensus, but now we'll make use of a noisy broadcast. And in our setting, the lieutenants here don't talk to each other, there's no feedback. So there is no need to sort of model the malice on the part of the lieutenants. We just need to worry about the commander being potentially malicious. That's what. Now, this line of replacing or sort of asking for information theoretic security in cryptography, relying on stochastic resources has a long history. Now, there is work on secret key agreement and privacy amplification, oblivious transfer, or even secure computation in general, big commitment, and even Byzantine agreement. So I'll come to this point later. And here's a plug for a book, nice book by Himanshu Tyagi and Shun Watanabe, which has a survey, it's forthcoming book, it's a survey of all of these and among other things. I'm not sure if Himanshu is in the audience. And there's a lot of other related work in information theory literature, not directly related to what we formulated, but certainly on privacy and security, starting, of course, with Shannon's seminal work, where we had an external adversary, an eavesdropper, who was passive, and there's work from wiretap channels. I also work on active adversaries, arbitrarily varying channels, a jammer, for instance, so communication in such instances. Also on communication in the presence of internal adversaries, like the one we are looking at, the Byzantine users, both active and passive, network coding and network information. Okay, so with let's let me get into the more formal definition of the problem. So we are going to consider a memory-less broadcast channel with finite alphabets and a code, rate R code of block length N is going to be just a map from the set of possible messages to vectors of length N, input vectors of length N. That's for the sender, the encoder. And for the decoder, these are maps from the decoder outputs of vector outputs of the channel back to the set of possible messages. Now remember what we wanted to do. When the sender sends a code word, we would like the decoders to agree on the message corresponding to code word. When a non-code word is sent, we just want it. So to say this formally, we define the probability of error as a maximum of two terms. First, corresponding to the honest behavior of the sender. So if the sender sends a valid code word, we would like the decoders to agree upon. So we'll look at the probability that both the decoders don't end up recovering the same message, and we'll maximize overall possible messages. And this second term is when the sender potentially deviates from a code word. Then we look at the probability that both the probability that the receivers don't agree, don't arrive at consensus, and we'll maximize this over all possible inputs to the channel. Okay, so let's then define, as one would usually do in such problems, the rate of communication with consensus that is achievable. We'll say that rate R is achievable if there is a sequence of such code such that the probability of error goes to 0. And now this is something we usually don't worry about how fast. The definition is usually not sensitive to this, but it turns out here it will be. So I'll come back to this point later. How fast is a point that I'll come back to. And Byzantine capacity is going to be the supremum of all rates that are achievable with consensus. And clearly, we are asking for something more than just the common message problem. We want consensus as well. So the Byzantine consensus capacity is upper bound, can be at most the common message capacity. Now, as you're looking at these, you might be thinking about other possible ways of formulating it. Instead of maximum here, what if we have an average error criteria? Our encoders and decoders were deterministic. What if they have private common randomness, or the decoders share some secret key, for example? It turns out the definition here is robust to all such variations one might think of. I'm not going to get into these. Who's interested, please look it up. Okay. So with that, what questions are we interested in today? So we'll be asking which broadcast channels allow communication with consensus, and what is the capacity of consensus for such channels. So let me pause here. If there are any questions, please feel free to ask on the setup or anything else. I don't see any questions, but feel free to interrupt. Okay. So before we answer these questions, let's start with a potentially simpler question. This is one-shot consensus. We're not really trying to do any communication here. We're going to make one use of the channel. We have no idea what the sender might do. Sender might send some input symbol. We have no control over that. We would like to both the receivers to agree upon this a common random variable. What is that common random variable that both the receivers can agree upon after seeing their channel? Let's try to answer this question. So to do that, it is convenient to look at a graph, a bipartite graph, where alphabets are the output alphabets of the two receivers. So I'm going to put an edge between two symbols here, Y1 and Z1. If there's a positive probability that they occur together under some input symbol here is X1. Okay. So let's put all those edges. And then we'll do the same thing for the other input symbol X2. So now we have this bipartite graph. Let's look at the connected components of this graph. Now it's, if you think about it, it's clear that both the receivers can agree upon the connected component of their outputs, okay, of their channel outputs. In particular, let's look at receiver 2. Suppose the receiver 2 observes Y3. Then it doesn't know whether receiver 2, receiver 1, okay, receiver 1, suppose it observed Y3. Then it doesn't know whether receiver 2 observes Z2 or Z3. It could have, receiver 2 could have observed Z2 if sender sent X1 as the input, or could have observed Z3 if sender sent X2 as the input. But one thing is clear for receiver 2, that receiver 1, that receiver 2's outputs are definitely in this connected component. And same thing for receiver 2. For example, if it observes Z3, then it is confused about what precisely the output at receiver 1 was, but it certainly knows that it belongs to this connected component. So that means that the connected component is something they can both recover. And so the induced channel from the input to the broadcast channel to the connected component index is a common channel, is a channel whose output they both can agree on. So this immediately presents a solution to our problem, an achievable solution. By the way, I should mention that for those who have seen Garch and Körner's common information for distributed sources, they will see that this is just the channel analog of that, what we are describing here. So what is that solution? The solution is just use a point-to-point code for the common channel. And since both the receivers can recover the common channel output, they can agree upon that. If they run the same decoder on it, the point-to-point channel decoder, they are bound to agree on their outputs. So irrespective of whether the sender sends a code word, valid code word, or whatever. So this means that the Byzantine consensus capacity is at least the point-to-point capacity of this common channel. So natural to ask, wonder, are these two the same? In fact, this was our initial conjecture when we started working on this problem. And we thought it was a matter of showing any possibilities of the converse. But it turns out the answer is you can, in fact, sometimes do better than the point-to-point capacity of this common channel. However, there is a connection to the common channel. It turns out that if the common channel has zero capacity, so if it's a trivial channel, common channel, then the Byzantine consensus capacity must be zero. So Byzantine channel capacity is positive if and only if the common channel capacity is also positive. Okay, any questions so far? All right, let me soldier on. What I'm going to do now is try to convince you of this statement. The argument is very elementary, so I can do it on these slides. And then we will look at what exactly is consensus capacity. So we have the first answer to our first question. What are non-trivial channels? What are broadcast channels which allow communication with consensus? Precisely those which are with a non-trivial common channel. I'll try to convince you of this fact, and then we will look at the consensus capacity. So mainly what I want to convince you is that if common channel capacity is zero, then no Byzantine consensus is possible using such a channel. So to do that, let me look at this example of a binary independent erasure broadcast. So here the same input is being erased independently by two independent erasure channels, and that's what the receiver is. So now if you sort of try to put down that graph, bipartite graph we talked about, we'll see it's just one big connected component. So there is no common channel. The common channel is trivial, and there is no common channel capacity. So let's try to see why is it that we cannot, in fact, what we're going to show is that we cannot even send one bit over this channel with consensus. Let's try to see why that is the case. For concreteness, I'll take the erasure property to be half. Okay, so let's suppose that we're trying to send just one bit, and suppose the code words for bit 0 is all 0 vector and bit 1 is all 1 vector. The argument is more general than this, but let's just go with this. So when all 0 vector is sent, we want both the receivers to agree upon decode to 0. Now, imagine the sender sends the same code word except it flips the first bit to 1. Let's think about what would happen. So imagine one of the receivers, for one of the receivers, this bit was not erased. So it sees this one and it knows that and it sees a bunch of other zeros also, maybe erasures in between. It knows that certainly the sender is deviating from agreed upon protocol. So at this point, the receiver should feel free to declare an error or output 1, for instance. We didn't all, but however, there is a problem. So right now, if all we wanted was communication, then we wouldn't have minded what the receiver may not have. However, we need consensus. So this receiver who's observing this 1 doesn't know whether this bit 1 made it all the way to the other receiver also. Potentially the other channel erased it. So for the sake of consensus, it should continue doing what it was doing earlier, which is to output 0. Otherwise, there's a danger, there's a half probability that the other channel erased this bit. And for the other receiver, of course, when this bit is erased, everything looks as if all 0 vector was sent, right? And there will be a lack of consensus. So the point I'm trying to make is that making this flip of 1 bit will have little effect on the output distribution. I'll try to convince you a little more detail as we go along. It turns out we can continue doing this. We can keep making these incremental changes one at a time and argue that there will be very little change to the behavior of the joint distribution of the output. And then if we keep going like this, what we see is that, okay, over here, they were, they had to output 0. Well, yeah, in n steps, we've reached all 1 code word. And therefore, with this much probability, they still need to output 0. And if the probability of error is falling faster than 1 over n, then that means that with overwhelming probability, they are still, the decoders are still constrained to say 0, even when the all ones vectors. And this is where the contradiction is going to come from. Now, let me quickly take you through this thing that I told you about, that when you flip one bit, there's little effect on the joint distribution of the decoder output. So let me convince you of that fact in a little more detail. So let's take some vector x and take one of the positions, say the kth position, and flip the bit over there, and it's called x. So the claim is that, let's focus on the first receiver. The probability that the receiver says 0 under x and under x tilde, when the inputs are x and x tilde, these are going to be nearly the same. Now, why is that? Well, the reason is, let's look at what happens to the kth bit. So let's condition on what happens to the kth. With half probability, that bit is erased, with half probability it's left unerased. So the probability that the output is 0 for the first receiver is like so. And similarly, when the other vector is set, where only the kth position is changed, and these two terms share, so we're asking, are these things the same? They share one term here. So what I'm really asking is, are these two terms the same? So now, as as your intuition was, we will bring in the second receiver. In particular, we are worried about this bit being erased for the second receiver. So if you look at the second receiver, the event where the first receiver receives the bit and the second receiver gets an erasure here happens with probability 1/4. So therefore, these two terms cannot significantly differ if you want consensus. So we are moving along this edge, we are looking at this edge here in the bipartite graph. Now, same consideration, but with the second vector. So that's, we are looking now here along this edge. Again, we can say the same, which means that both of these terms must also be nearly the same. So here what we've done is we've sort of moved through this path on this bipartite graph. So you can imagine what would happen if a bipartite graph was more elaborate. We would be taking a path, maybe moving a few times back and forth. But the idea is this. So what we can conclude is that under both these, the first receiver must indeed say 0 with nearly the same probability. And since both receivers need to be in agreement, we can also say the same thing, that both of them need to say 0 with nearly the same probability. And this is what we were making use of. So what we have said is that if the probability of error falls off faster than 1 over n, then we have a contradiction. We can't even send a bit using this. Now one might wonder, is this an artifact of this very elementary proof, or could one have done a more careful proof to sort of say this even when the probability of error falls off faster, or is it something more fundamental? It turns out, in general, there is a phenomenon here that this is not an artifact of the proof. There are examples of channels where the common channel capacity is 0, and therefore, this sort of argument can still be done. But where we can achieve positive rates of communication with consensus if we are willing to work with a slower decay of the error probability. This is an interesting phenomenon which we don't usually see in other network information theory problems. The capacity is sensitive to how the probability of error decays as the block length goes to 90. And what we study is the natural region. where for achievability we will get properties of error which as usual fall off exponentially with the blocking. But for the converse, we will insist that the probability of error decays at least or faster than linear. And the regime where probabilities of error fall off slower than this is in fact open. We have examples, as I mentioned. So this is how we define capacity. Just closing the loop on the definition. By the way, I must mention that for this particular channel, this particular independent erasure broadcast channel, it turns out that one bit cannot be sent even if we allow the probability of error to decay arbitrarily slowly to end. So we can, what I'm trying to say is for this particular channel, we can in fact get a stronger converse. And that works for a class of channels, but not in general. In general, this is a real phenomenon. Okay. Any questions so far? All right. So then let me move on to so we looked at a converse argument essentially. I convinced you hopefully that when the common channel capacity is 0, no communication consensus is possible. Now let us see how we can get consensus. So to do that, again, we look at an example. So this is, of course, a trivial example where we have just a common channel, binary erasure channel. So clearly here, Byzantine capacity is just the point-to-point capacity, which is 1 minus P. This is a binary erasure channel, erasure probability P. Now let us imagine giving the receivers one more look at the input. But the second look is over independent erasures, independent erasure channels. So this is our what we call two-step erasure channel. Now the effective channel from the input to each receiver is a binary erasure channel with erasure property P times, and both the common channel and this independent erasure, both of them need to erase for the bit to be really erased, right? And that happens with probability P times 2. Okay, so let's ask ourselves. So as we said, clearly the common channel capacities that we can achieve, that is 1 minus P. Can we do any better? Can we do strictly better? Now, recall that when the common channel erases with probability 1, that is, there is no common channel, then we just saw that this is pretty useless. Independent erasures is useless. So Byzantine consensus capacity was 0 for that case. But it turns out when there is a non-trivial common channel, P is less than 1, erasure property is less than 1 for the common channel, then we can do as well as possible. We can get all the way to 1 minus PQ, which is the common message capacity, also the point-to-point capacities of each of these channels. By the way, if you're wondering, I should mention that it is not the case that whenever Byzantine capacity is positive, we always get the common message capacity. That is not. So in the paper, we give an example, non-trivial example of a Byzantine of a channel whose Byzantine consensus capacity is strictly in between common channel capacity, common message capacity for the broadcast channel. So let's ask ourselves, how can we achieve this 1 minus PQ? So this is the sort of achievability idea we want to look at. So can we use what we would normally use for achieving the common message capacity? So what is that? We'll just use an erasure code, capacity achieving erasure code, and use erasure decoding at the receivers. So what I mean by erasure decoding is the decoder will look for a unique code word which is compatible with its received bit. That is a unique code word such that every received bit is consistent. It matches the bit in the code word. So that's erasure decoding. Can we use that? That certainly achieves the common message capacity for this channel. We use a erasure binary erasure code of rate approaching 1 minus P2. Well, that turns out wouldn't work. So here's a simple attack for the adversary. Suppose adversary takes a valid code word and flips, let's say, the first bit and sends this as a malicious adversary. Now, suppose that the erasure, the common channel erases this first bit, and the private channel to the first receiver also erases the first bit, but the one to the second receiver keeps it, doesn't erase. And this happens with a constant probability. There's P for this and Q times 1 minus Q. So this happens with the probability we should worry about. It's not a vanishing problem. Now, for the first receiver, as you can see, it's as if the first bit didn't exist where the flip happened. So everything would look consistent with this code word and it should accept this message. Whereas for the second receiver, because it sees a 1 here, it's not compatible with this code word. M is not even a candidate. It's not going to accept. M is going to reject. Yes, but this suggests an obvious fix. What we should do is we should tolerate some errors at the decode. We should allow the sender to make a few flips here and there. We should still tolerate that. Let's do that. Let's tolerate some errors at the decode. Okay. But this still leaves open a possibility for attack by the sender. So what the sender can do is it can flip just the right amount of bits in the code word with the hope that the channel would erase enough of these bits so that it falls inside the boundary of tolerance for one of the receivers and will keep it outside for the others. And this is not a hypothetical attack. It turns out you can actually construct such an attack against this. Okay, but here we can make use to sort of prevent this sort of an attack. We can make use of the common channel. So the idea is that let us see what would happen, right? So if the the sender flips a sufficient number, right? We are allowing ourselves some tolerance. So it needs to make sufficient number of erasures to kind of engineer such an attack. Now, if sufficient number of flips are made, it is bound to show up on the common channel. And on the common channel, the receivers will accept no tolerance. There will be no tolerance. They will check for compatibility with the code word with no tolerance. Now, under such an attack, both the decoders will reject. In the absence of the common channel, this sort of a thing is not possible. So this is where we really need to make use of the common channel. Okay, so I just kind of took you through some possible attacks and so on, but it turns out this sort of covers. So of course, we should allow for all possible attacks. So we have a kind of detailed proof which handles all possible behavior of the adversary. But this is the basic idea. So our decoder will work something like this. It's going to look for a unique message such that the code word is compatible with the common channel output and such that it is within a tolerance boundary from the received vector, right? The overall received vector. So, and of course, if no such thing is found, it outputs an error. And for such a decoder, we need certain properties from the code. In particular, we need to make sure that these tolerance boundaries don't intersect, but the tolerance is just going to be a small fraction, and this doesn't really result in a rate constraint. The second condition here is somewhat technical. So what it says is that from any vector x, if you look around, the number of code words that you see at a certain having distance, we can give an upper bound. Basically, this is an appropriate version of a packing lemma for this problem. And what it does is that it says there should be no crowding of code words. If there's a crowding of code words at some kind of resolution, then it can result in an attack. So I'll sort of leave the details for you to look up if you're interested. So again, yeah, so as I said, yeah, this is not just against the attacks that I mentioned, but can show that any possible strategy the sender, malicious sender may take, you can still get consensus with. So any questions on anything so far? Okay, so let me continue. So this brings me to the general result, the result we have for general channel. So I'll try to describe the result. It turns out we cannot make use of all the input symbols of the broadcast channel to build a consensus. We define what we call the effective input alphabet of the broadcast channel. So what we mean by that is these are the symbols corresponding to the vertices of this convex polytope, which is the convex hull of the PMFs, the conditional PMFs of the common channel, corresponding to different input symbols. That is, this is the convex hull that is produced by the row vectors, if you want, of this common channel of the common channel. We take the row vectors of the common channel and then consider their convex hull and see what the vertices are. And it turns out we want to only use these symbols. The issue is the following. It turns out if you use the symbol which is not one of the vertices, then there is a substitution that the sender can do, malicious sender can do, an appropriate probabilistic choice, in this case from one of these three letters, which will leave no trace at the output, no evidence at the output of the common channel. And this in turn will prevent the receivers from arriving at a consensus on whether such an attack is going on and having an overall consensus. So the theorem, the capacity theorem, looks something like this. So there's a maximization being carried out over input distributions which have supported only on these symbols corresponding to the vertices of this convex polytope. And then there's a minimization of the mutual information to each of the receivers. The true, we're not now talking about the common channel. It's good to compare this with the common message capacity expression, which some of you know. There, the difference is this. There's a maximization in the common message case. We could maximize over all distribution just supported over the entire alphabet, input alphabet. Whereas for the Byzantine consensus, we are restricted to maximizing over distributions of support on these effective input alphabets. Turns out there's one more complication. You may have symbols, multiple symbols which are sitting at the vertices. When that happens, we need to allow the adversary the option of taking the probability mass which is sitting here, the input distribution, probability mass associated with the input distribution, and splitting it among these symbols. So there is an extra minimization. So this is in fact the final version of the capacity theorem. So I'll quickly mention the ideas behind this theorem without getting into too many details. So what the Converse follows from something like this. We consider a malicious sender who, instead of sending the code word, sends the code word through a channel and then sends the result of the channel into the true channel. Right? So this is something internally simulated by the malicious sender. What is this channel? These are channels which leave no trace on the, no evidence on the output of the common channel. Now, for such channels, we can argue, if such an attack is mounted, we can argue that the receivers must still agree on this sent message. And the way we prove this is, along the lines of the sort of generalizing what I showed you earlier, by introducing this channel one step at a time on each of the elements of the code word vector. So we introduce it first to just the first element of the code word vector, leaving the others without it, and then arguing that this must still be true with 1 minus some k times p and so on and so forth. Right? So we do it one step at a time. I'll sort of not go into the details, but this is basically the difficulty. That is, this sort of an attack cannot be detected by the receivers in a manner where they can still achieve consensus. They individually, they may be able to tell something is going on, but they can't arrive at achieve consensus. Okay, so, and for the achievability, again, at a high level, the idea is very much the same as what we saw earlier. We just need to do appropriate notions of distance. So no longer having distance, we need an appropriate notion of distance and an appropriate notion of what it means to be compatible. I won't go into the details here, but at a high level, it's a very similar intuition as in the binary erasure, the two-step erasure. So this is what gives us our result. Okay, so with that, let me summarize what we have seen. So I talked about the capacity of communication with consensus in a broadcast channel. We saw that feasibility of such consensus using a broadcast channel depends on whether a non-trivial common channel exists or not. We saw some Converse and achievability ideas. And as I mentioned, these results generalized to more than 2 receivers. And we noticed an interesting phenomenon. Capacity definition is in fact sensitive to how probability of error decays as the blocking goes to infinity. And several things were left open, in particular, I mentioned what is the capacity in the regime where probability of error may fall slower than 1 over n. That is a question we have to address. And that of code constructions and more general channels. By that I mean, currently we assume that the channels are known to everybody, all the players, and the code assumed the knowledge of this channel. If, for instance, channel could be, there could be uncertainty about this channel, it could be from a class of channels, and which particular channel is realized may even be controlled by the adversary, for instance. So in such cases, it'd be interesting to look at how these ideas generalize. Another thing an important thing we didn't do is to allow any interaction between the receivers or between the agents in general. Right? And this, if you allow such things, the conclusions will certainly change. In fact, the impossibility result that I showed you changes. In particular, the channel I showed you today, it turns out it is possible, the independent binary erasure channel, broadcast channel, it is actually a useful resource to do Byzantine consensus if interaction is allowed. So the results change. So this is a question that we are currently investigating. And we can also investigate this question in what is called a source model, where the parties, the agents get some correlated source. So this could even be pre-computed and provided to them in order to facilitate consensus. And then they just try to interact over this network. The question could be, can we get around the impossibility result for Byzantine consensus that we saw? Which kind of correlated sources would allow one to do that? And what sort of channel models would allow us to do that? So this particular question about the source model was in fact studied earlier in a limited sense. And there's certainly something we are also looking at now. And I should, in fact, thank Himanshu for pointing me to this reference, which we weren't aware of while we were, as we started working on this. Okay, so with that, let me close. Thank you for attending, and I'm happy to take questions.
Thank you, Professor Vinod, for the engaging talk.
Thank you.
So if there are no questions, maybe we can close the session.
All right. Okay. Thank you very much. Thanks everybody for coming.
Thank you for being a part of the seminar series. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. Thank you, everyone, and have a great evening.